So thank you, Mr. Chairman. So, ladies and gentlemen, first I would like to thank the organizers of this conference to invite me here, and very specifically Dr. Pizmintsev, who organized all of my trip. So it's a great pleasure for me to be back here in Yekaterinburg, because I was here first time 20 years ago, also on invitation of Dr. Pizmintsev, and yeah, it was not only 20 years ago, but also 20 kilos ago for me. So, and it's fantastic to be back here in this great place. So I also thank Dr. Pizmintsev for having, I don't speak Russian, unfortunately. I also don't understand it, but I understood that he talked a little bit about texture. So about the importance of crystallographic texture for production of pipeline steel. So it is of course important to be able to control the crystallographic texture if you manufacture metals. And I'm going to give a few examples today, and also of the physical metallurgical mechanisms behind the texture formation, because, well, in technology you have not reached really progress if you do not, unless you understand what you are doing. So, okay. So let me first start out with illustrating what is the importance of texture studies. Why do we still study texture in steel? Well, or in other metals, of course. Texture, in the first place, it is a major source of anisotropy. So very often material properties have anisotropic behavior. If you, for example, measure the strength in the rolling direction of a steel sheet, it will be different in the transverse direction. And very often texture has something to do with this. So I give here a number of examples. Mechanical properties, of course, probably the most familiar, but also physical properties such as elasticity constants, dilatation, surface energy. All this may be anisotropic properties or chemical magnetic properties. In summary, you could say that all properties with crystal anisotropy in the single crystal, they will be texture dependent in the polycrystalline material. So if, for example, the elastic modulus is different in a cubic crystal in the 111 direction and the 100 direction, unless you have a textureless sample, it will introduce anisotropy in the macroscopic polycrystalline sample. More and more also it becomes a important to understand texture if you want to better control production, because actually the texture aspects or the crystallographic aspect, normally it is a part of our theoretical development of understanding what's happening during processing. So if you process steel, for example, you have a number of successive stages. You go to solidification, phase transformation, plastic deformation, and so on, recrystallization, thermal activated processes. All these processes, in order to understand them, we need theories. So we need models, and crystallography is a part of these models. And therefore, if we really want to have a complete theory, it also will involve a understanding of the texture of aspects of those theories. And in industry, this is important because, for example, if you want to understand the thermomechanical conditions of production, then you better also look at the texture. or if you want to have more accurate structure property relations. That's why sometimes I call texture is part of the DNA of the metal. And of course, there is a whole evolution going on in substituting trial and error empirical knowledge to with real physical models. Okay, sorry. So let's now have a look at an example. So perhaps one of the most traditional example is texture formation during cold rolling and annealing. So let's assume for a moment that rolling is a simple plane strain compression of deformation, and then after rolling we have a rolling texture. So here you see these are EBSD measurements. This is an initial hot band structure, in fact, and this is after cold rolling. And you can see that the hot band structure, in fact, this is a phi2 45-degree section. I will explain it a little bit more. So actually it's a very weak texture, and it has maximum on these three components. So if you anneal this, then you find, if you cold roll this, you get this type of texture, which is a much stronger texture. So which is what we call an alpha gamma fiber texture. I come back in a moment to this. So I gave you some examples of what we call the phi2 45-degree section of Euler space. Normally we represent textures with orientation distribution functions. These orientation distribution functions give you the intensity of the texture components in Euler space. So each point, so normally it's a three-dimensional space. Fortunately, if you want to describe cold rolling and a typical cold rolling and annealing texture of low carbon steels with BCC crystal structure, we can do with one section of Euler space, phi2 45-degree section. Why is this? Just by pure luck. Nature is favorable to us. So we don't need the three-dimensional description. We can just do with the two-dimensional section. This is only the case for cold rolling and annealing. So if you do wire drawing, for example, or extrusion or forging, then textures may be totally different, and you need to consider the real three-dimensional Euler space, but not in this case. So here, typically for the cold rolling texture is that we have two fibers. We have an alpha fiber, which is the set of orientations that have the 110 direction parallel to the R rolling direction. And we also have the gamma fiber, so which has the 111 orientations parallel to the normal direction. Here you can see that, for example, there is a maximum here on the alpha fiber of 8, and this maximum more or less is situated at this component, 112 minus 110. And these numbers, 8, 5, 6, these are intensity levels. We compare them with the random texture. So if you would have a powder sample, for example, then all the levels would be equal to 1. So here 8 means 8 times more intense than in a powder texture sample or in a textureless sample. So this was for cold rolling. Now, normally we also have recrystallization if you deal with low carbon steels, and then during recrystallization you get the transformation of the alpha gamma fiber texture typically to a gamma fiber texture. So this is the result of recrystallization and grain growth. So now we basically have the gamma fiber. So here we had the alpha gamma fiber, now we have the gamma fiber. These textures, they are very suitable. So this is the natural behavior of low carbon steel. So these textures are very suitable for deep drawing. If you see steel car bodies, it's very likely to have this type of texture. Actually, steel industry proclamates this as one of the big successes of texture control, but, well, let me tell you a secret. Steel industry was helped a lot by nature. The natural evolution of texture is to go to the FCC, to the gamma fiber texture. Okay, so let's have a look now a little bit what happens during recrystallization. What are the physical mechanisms involved? Well, texture, so we're going to have a look at the early nucleation texture. This is the stage of, the initial stage of nucleation. So in thermodynamics tells us that the driving force for recrystallization is the stored energy of plastic deformation. So of course recrystallization is traditionally described as a process of nucleation and growth of recrystallized grains in the deformed matrix. Now, the word nucleation, we have to be careful here because in the context of recrystallization, nucleation is not the classical nucleation in the thermodynamic sense of the word, like when you have solidification or you have a phase transformation. Actually, what we mean with nucleation here in this context is the recovery of the deformed structure. So what it means that you have to create a crystallized volume which is viable for growth in the deformed matrix. Therefore, it needs to be of a critical size, it needs to be free of dislocations, and it needs to have sufficiently mobile boundaries. So these are the three conditions that must be fulfilled to have a recrystallization nucleus. Now there has been in literature described various mechanisms of nucleation which are of importance. Very well known is the so-called bulging mechanism or the strain-induced boundary mechanism. This is where you have a relatively dislocation-free cell which bulges out in the neighborhood of a cell with higher dislocation density, with higher deformation energy. So then you also have another mechanism which is subgrain growth. So in subgrain growth, you have in fact a cell which starts growing abnormally. And it's a little bit like abnormal grain growth, but on the level of the subgrains, not on the level of grains. Now beware that this mechanism, in fact, you see this has already connotations for texture, because here this mechanism is more favorable to happen in grains with low stored energy. So you will see that a dislocation poor region or dislocation free region will grow into a dislocation intense region. So this is related to orientation effects, whereas this type of mechanism is more favored in regions with higher stored energy. Then you also have another mechanism which is subgrain mechanism. So subgrain coalescence. You have two cells, in fact, two subgrains which are separated by a subboundary, so which normally has a small misorientation, and by diffusion effects of dislocation climb, so this dislocation boundary will disappear and this merges into one large subgrain which then starts growing into the deformed matrix. Okay, so all these mechanisms, as I said, these mechanisms are orientation dependent. Why? Because the stored energy is dependent of the orientation. So this, for example, can be visualized by orientation contrast microscopy. You know the EBSD, we can collect orientation data on the local scale with resolution of scanning electron microscopy. Let's say EBSD, typical, the highest resolution you can get is 10-20 nanometer. Now there are various ways how to extract stored energy information from EBSD data. So one of the ways is to link the cell size, D, or the subgrain size, and the misorientation between cells to the stored energy. This is the famous relation of Reed-Shockley, in fact, which gives you the relation between stored grain boundary energy and misorientation and cell size for low energy, low angle grain boundaries. And this data can be obtained from EBSD data. So they can be determined from orientation contrast scans, and we can calculate the stored energy. Oh, this is a mistake. Yeah, if you turn your head to the right, what is written here is the Naies tensor, which gives you the relation, in fact, between the crystallographic curvature and the density of geometrically necessary dislocations. What geometrically necessary dislocations are statistically the dislocations that give you a non-zero closure vector, non-zero value of the closure vector of the Burger circuit. So if you have a group of dislocations, you sum all of their Burger's vector, the total sum, or the total integral, so to say, that remains over, this is the closure vector of the geometrically necessary dislocations. It are these, this is a statistical quantity. You cannot say of one specific dislocation, you are a geometrically necessary dislocation. No, it's a statistical property of a group of dislocations. And this property is responsible for accommodation crystal rotation. And this crystal rotation, this misorientation, we can measure. And therefore, we can derive from EBSD data density of geometrically necessary dislocations. Not the total density of dislocations, because the total density will be the geometrically necessary dislocations plus the statistically stored dislocations. But this we cannot, this information we cannot obtain by EBSD. So here we worked out a model for that. For example, this is an IF steel, and this is a titanium carbide and titanium nitrides. And you can see that this is slightly deformed, and in the vicinity of these particles you have strain increase. So in fact, this is the microstructure, this is the crystal orientation, or and also the density of geometrically necessary dislocations. Now this is a map, the kernel average misorientation map. It's also extracted from orientation data. It's calculated on the orientation scan. What is CAM, or kernel average misorientation? Oh, I thought I had a picture of that. Yeah, here. So actually, if you have an EBSD scan, you measure for each pixel the crystal orientation, and the CAM value is the average misorientation between a certain pixel and a number of neighboring pixels. This can be first neighbor, second neighbor, and so on. So that's why we call it, so if you make the average between all these misorientations, then you have the average CAM value of the central pixel. So we argue that this is related, the curvature, the lattice curvature that you measure in this way is related to the density of geometrically necessary dislocations. And for example here, this is an example of a fatigue fracture, and you can see that around this fatigue fracture you have a strain zone, a crack tip plasticity zone. And so this was aluminium, by the way, but that's not important. Okay, so let's now turn back to our, this is an ultra-low carbon steel, only 20-30 ppm carbon. For the rest, technically pure iron, so to say, 70% cold rolled. It has a nice alpha-gamma fiber texture. Okay, so this is the distribution of the CAM values. So obviously there is a high peak here at this low spectrum because of the high density of low angle grain boundaries. But what is interesting to see is that if we take the partition here at the high end tail, you see these are the gamma fiber orientations. Where if we take the partition here at the low end tail, these are the alpha fiber grains. So CAM is a measure of stored energy, of dislocation density, geometrically necessary dislocations. So, okay, so that's my argument here. So here we have a high energy region, and here we have a low energy region. Now we can understand the reason why this is, because we can do some modeling based on crystal plasticity methods. What is crystal plasticity? Crystal plasticity will tell you how the macroscopic strain on the level of a workpiece is accommodated by individual crystals in the polycrystalline set. For example, one of the basic theories is the Taylor theory, already from 1938, which allows us to calculate what are the active slip systems in each of the individual grains. And the Taylor theory, so there are various variants. I'm not going to emphasize on this. So now there are more recent models, but still based on this original idea of Taylor. Very important is the total dissipated plastic power. This is in fact the energy that is dissipated during strain. Now if you assume, because the largest fraction of this energy is dissipated as heat, but a certain fraction, 5–10%, will be stored in the material as residual dislocations. So that's why we can, this value, which we can calculate by the Taylor theory, and if we make it dimensionless, we have the Taylor factor, it's called M. Actually, it's the dissipated power divided by a macroscopic measure. So this Taylor factor is a measure of the stored energy, or we can interpret it as a measure of the stored energy. And it will be dependent on the crystal orientation and on the strain modes, of course, the type of displacement field that you have. For example, for plane strain compression, the example that I was showing, we have rolling. So this is the strain tensor, and to the right, what you see is a texture map. It is a Taylor factor map. Sorry, it's not a texture map. This is not a texture. This gives you the distribution of the Taylor factor in the phi 2 45-degree section. You can see here that here we have a maximum. So here in this region, we have high Taylor factors. On the gamma fiber, do you see the correspondence with the experimental data that we found that these are high CAM value orientations? And here we have low Taylor factor values. It goes down to 2.2. This is minimum and this is maximum. So this is a theoretical calculation of the stored energy. So, and then we can use this, so to say, to have a model of the recrystallization texture, because suppose now that we filter out only the high stored energy. Suppose that we assume that only orientations with high stored energy can recrystallize, the ones with the highest driving force. So if you, from this texture, which is the experimental deformation texture, if you now filter out all of the orientations with the high Taylor factor, that's what you get. You see? This is the gamma fiber texture, which also spreads on the rotated cube component. So this can be the basis of a recrystallization model. Now, it is sometimes more complicated because in real life rolling, you do not only have plane strain compression. You may have a combination of plane strain compression and surface shear also. So then the strain tensor becomes more complicated. And here I have such an example in which we did a roll. This was hot rolling, which on an iron 1.23% silicon sample, it was asymmetric hot rolling. That means that the rolling diameter of surface and bottom roll was different. And then this is the deformation texture. You see, this is very much different from our typical alpha-gamma fiber texture, from plane strain compression. So I'm not going to explain this. What is interesting to see is that also this is the recrystallization texture. This is the texture after recrystallization, and it looks a little bit exotic. So we're not very familiar with this. But now we have a different type of displacement field, a different type of strain tensor. So because also we have a shear component now, which was not there before. And if we actually, based on a paper, we calculated the strain tensor, and now this is our Taylor factor map. You see, it looks totally different. You see here that in this region, the blue region, we have low stored energy grains. And this is quite peculiar that in this case, the maximum of the texture corresponds with the minimum of the Taylor factor. Whereas in the previous example, it was just opposite. And what was different between the two examples? Well, the strain mode was different, but I think more important, the temperature of rolling was different. Here we were rolling at elevated temperature. By the way, this steel does not, at the temperature that we rolled, was still in ferrite because of the silicon content. Okay, so why is there a difference between high and low stored energy nucleation? Well, this is the subject of present research. I don't have a conclusive answer to this question. But for sure, the deformation at room temperature versus deformation at elevated temperature plays a role. And low strain versus medium and high strain during rolling also plays a role. Because I didn't emphasize this, on the asymmetric rolling experiments, the total strain accumulation was much lower than in the conventional rolling process. And I don't have time to speak about it, but we also could discuss the role of dynamic recovery. So I come to my conclusion saying that I hope that I could convince you of the importance of texture control in steel sheet manufacturing. We discussed mechanisms of orientation selection during recrystallization, or more precisely during nucleation of cold rolled and warm rolled steel. We expanded some theoretical understanding by making use of crystal plasticity modeling of recrystallization texture, and I finished with an open question on the high stored energy versus low stored energy nucleation. So thanks for your attention, and I'm ready to answer your questions.